All right, we're going to discuss the chapter 27 homework examples. So most of these problems, I've only got 3 problems. 2 of them come from Physics for Scientists and Engineers by Serway and Jewett, 10th edition. The other one having to do with Kirchhoff's rules. It comes from Giancoli, Physics for Scientists and Engineers, the 4th edition. So I skip any problems from 27.1. Just be aware that there is internal resistance in a power supply and in a battery. Most of the time we neglect it, but we don't concern ourselves with it. It's pretty small compared to the values that we're working with. So let's start off with reading the problem statement. A battery with a EMF of 6 volts and no internal resistance supplies current to the circuit shown in the figure below. When the double throw switch is open as shown in the figure, the current in the battery is 1 milliamp. When the switch is closed in position A, the current in the battery is 1.2 milliamps. When the switch is closed in position B, the switch in the circuit is 2 milliamps. What are the resistances? So this is what we're looking at. This is the switch in the open position, and you can see that it all of these internal lines and resistors, it ignores those. So this is what it looks like when we're in position the position shown with the open position. In position A, it's this is the circuit here. You have R1, and then the R2s are in parallel basically, and then you have R3. And then when you switch it to B, basically it takes out one of the R2s, it takes out this R2, and it takes out this R3. It just bypasses it, and all you have is R1 and R2. So let's clear those, and these are the circuit diagrams. The caption says circuit diagram with the switch open, the switch in position A, and the switch in position B. With the switch in the open position, the total resistance is 6 volts divided by 1 milliamp, 1 times 10 to the minus 3 amps, and you get 6 kilo ohms. So we know that the formula for the equivalent resistance is just R1 plus R2 plus R3, and that's equal to 6 kilo ohms. So we have our equation 1. With the switch in position A, the resistance is 6 volts divided by 1.2 times 10 to the minus 3 amps, and we end up with 5 kilo ohms. So the equation for the equivalent resistance is R1 plus, then we have to do the little parallel combination, and it's the reciprocal of the sum of the reciprocals, 1 over R2 plus 1 over R2 plus R3, and that equals R1 plus R2 divided by 2 plus R3 equals 5 kilo ohms. Prove to yourself that parallel resistance comes out to R2 over 2. So that gives us equation 2. Now with the switch in position B, the resistance is much simplified. It's 6 volts divided by 2 times 10 to the minus 3 amps, and we end up with 3 kilo ohms. And the equation is very simple. R1 plus R2 equals 3 kilo ohms. Okay, now that we have those 3 equations, we can determine R1, R2, and R3. If we subtract equation 2, if we subtract this one from this one, this is what we get. R1 plus R2 plus R3 minus R1 plus R2 over 2 plus R3 equals to 6 kilo ohms minus 5 kilo ohms. So on the left-hand side, all we're left with, is this cancels that and this cancels that. And so all we're left with is the R2 over R2 divided by 2 is equal to 1 kilo ohm. The 6 minus 5 is equal to 1, so it's 1 kilo ohm. Multiply both sides by 2, and you're left with R2 equals 2 kilo ohms. And so there we've got the solution for for R2. Now, using this value of R2, we can get the value of R1 using equation 3. This is equation 3, R1 plus R2 equals 3 kilo ohms. So R1 plus 2 kilo ohms, which we just determined the value for R2, is equal to 3 kilo ohms. You subtract 2 kilo ohms from both sides of the equation, we get R1 is equal to 1 kilo ohm. So now we have R1 and R2. And now finally we can get R3 using equation 1. Here's the equation 1. It's just very simple. It's R1 plus R2 plus R3 equals 6 kilo ohms. So we plug in the values for R1 and R2, and we have 1 kilo ohm plus 2 kilo ohms plus R3 is equal to 6. So these combine to 3 kilo ohms. We subtract that. We subtract 3 kilo ohms from both sides, and we'll see that R3 equals 3 kilo ohms. And so in order, the three resistor values are R1 equals 1 kilo ohm, R2 equals 2 kilo ohms, and R3 equals 3 kilo ohms. And we got that just from setting up three equations and solving them simultaneously. All right, that's it for problem 1. This one's a little more complicated. This is the one from Giancoli, the 4th edition. So very simple problem statement. Calculate the currents in each resistor of 26-50, figure 26-50. This is 26-50. So there's a few loops that we can look at. I'm going to look at going out of the positive of the battery. So that puts me going in this direction and going in this direction. For, which I'm looking at this loop, I'm looking at this loop. Now we could have also looked at this outer loop, this here, but I chose not to do that. You can do that if you want. It probably would have been a little more complicated because you would have had 2 batteries in your equation. With this loop here, there's just 1 battery and 3 resistors. In this loop here, there's 1 battery and 3 resistors. So let's that's my reasoning. So there are 3 currents. The current through the 58-volt battery, this one, I1, the current through the 64 ohm resistor, I2, and I'm going to assume that it's going this way, and the current through the 3-volt battery, this one here. And the junction rule, these 2 will add up to this 1. So from Kirchhoff's junction rule, we assume that I1 equals I2 plus I3. There are 3 loops. There are 3 loops available for analysis, but let's use the 2 simplest, the left loop and the right loop, and not analyze each in a counterclockwise loop. That's what I just drew. So we have the, remember, if we assume the current in this direction, we have, whoops, sorry about that. We have plus to minus, plus to minus, plus to minus. So remember, as we exit the device, we take its sign. So if we start with the battery, it's a plus 58 volts, that's this, a minus I1 times 120 ohms, that's this one, and then I1 times 82 ohms minus, because we're exiting there, and minus, now we're calling this one I2, minus I2 times 64 ohms. So that, let's erase all this, let's make it bigger. That gives us our first equation. Now we look at the second loop. and we can do the same thing in this loop here. Now we've already assumed that the current is going up, so it's going up, it's plus to minus, and the on these, we're assuming the current is going this way, so it's plus to minus, and here it's plus to minus, and we're going to look at the exiting value. So we have the 3 volts, it's a positive 3 volts. We're exiting we're exiting the 25 ohms, so it's a minus I3 times the 25 ohms. Now notice as we exit the 64, it's positive, so it's a plus I2 times 64 ohms. And here, as we exit this 110, it's a minus, so it's a minus I3 times 110 ohms. Okay, let's clear that. So those are our 2 equations. Note that the change in sign for the 64 ohm resistor in loops 2 and 3 because of the assumed direction of I2. Now let's simplify loops 2 and 3. 58 volts equals I1 times 202 ohms. That's the those were the on the other side it was negative, but we've taken it to the right hand side, and the I2 was negative, so it becomes positive also, I2 times 64 ohms. Now if we do the same thing with the second one, is 3 volts equals I3 times 135, that's the sum of the 25 and the 110, minus the I2 times 64 ohms. Because it was positive on this side, it becomes minus on that side. Okay. Now let's substitute I2 plus I3 for I1 into the left loop. So 58 volts equals I2 plus I3 times 202 ohms plus I2 times 64 ohms. Now we can, if we look, we use the distributive property, and it becomes I2 times 266 ohms plus I3 times 202 ohms. Now that we have 2 equations and 2 unknowns, the 58 volts times the same as 58 volts times I2 times 266 ohms plus I3 times 202 ohms. And we have the 3 volts equals minus I2 times 64 plus I3 times 135. That's really just a rewriting of this equation here. Let's multiply the bottom equation by 1.4963 on both sides, and we do that so it'll we can get some cancellation. So we multiply the bottom by 1.4963, we get 4.489 volts equals minus I2 times 95.763 ohms plus I3 times 202 ohms. Well, if we subtract them, now we'll get rid of the I3. Then subtracting the bottom line from the top line, we get 53.51 volts equals I2 times 361.763 ohms. I'm leaving all the digits. We'll go to the significant digits at the end of all the calculations. Now that means that I2 is equal to 53.51 volts divided by 361.763 ohms. And that's equal to 0.1479 amps, or 0.15 amps with 2 significant digits, 150 milliamps. And I3, you can see, is 3 volts plus I2 times 64 ohms divided by 135, and that's equal to 3 volts plus the 0.1479 amps times 64 ohms divided by 135. And I should have an ohm there, but that's equal to 0.0923 amps or 92 milliamps, 0.092 amps. And finally, we have the I1 is the sum of I2 and I3, and we get 0.24 amps or 240 milliamps. Okay, and that's the end of the Kirchhoff rules. They're tedious, they're doable, but they can be tedious. And finally, we're going to get to RC circuits. Number 27, a 10 microfarad capacitor is charged by a 10-volt battery through a resistance R. The capacitor reaches a potential difference of 4 volts in a time interval of 3 seconds after charging begins. Find R. Okay, so I've drawn the circuit diagram. There's the 10 volts, the R, and the 10 microfarads. So there's the diagram. Now we can use equation 27.18. QT is equal to Q max times 1 minus e to the minus t over tau, where tau is equal to RC. And the knowledge that delta V equals the charge divided by the capacitance to find the resistance R of this circuit. So we just divide both sides by the capacitance. QT over C equals Q max over C times 1 minus e to the minus t divided by tau, which is RC. That's that equation there. And that becomes delta V equals delta V max times 1 minus e to the minus t divided by tau, or RC. So now this is just algebra. We divide both sides by delta V max. So delta V is divided by delta V max is equal to 1 minus e to the minus t divided by RC. Now we subtract the 1 from both sides, so we get delta V over delta V max minus 1 equals a negative e to the minus t divided by RC. Now if we multiply both sides by minus 1, we get e to the minus t divided by RC equals 1 minus delta V over delta V max. And now if we take the natural log of both sides, well, the natural log of e to the a is a. So it's minus, we're going to get minus t divided by RC equals the natural log of 1 minus delta V over delta V max. And we're multiplying both sides by C over a minus T, and we're left with 1 over R equals negative C times the natural logarithm of 1 minus delta V over delta V max divided by T. We take the reciprocal of both sides, R equals a minus T over C natural log of 1 minus delta V max. Now, all we've done is set up the equation that we're going to use to finally plug in values. And that's what we're doing in here. We go back to the problem statement. The T is 3 seconds. The V max is 10 volts and the delta V is 4 volts. And so we've got all of that information here. Oh, and the capacitor is a 10 microfarad. So all of that information we put in the equation. So R is equal to minus 3 seconds divided by 10 times 10 to the minus 6 farads times the natural log of 1 minus 4 volts divided by 10 volts. And you come up, put it in your calculator, and you get 587,285 ohms, or to 3 significant digits, 587 kiloohms. Let's see, I probably should have done it. No, there's 3, well, yeah, there's 3 significant digits in all of them. So there's 3 significant digits, 587 kiloohms. And that's the answer. And that's it for the examples. I hope this helps.